So, hi everyone. Welcome to Dude, Where's My C? I'm wondering where it is. A little background, obviously, Walter from the Foundation. I'm the security guy, official title, security engineer. But I basically do all things security for the Foundation and helping out the project as much as I can. That's helping the infra team secure infrastructure. That's answering any questions anyone has. And a lot of my time is spent thinking about sort of the broader questions when it comes to Rust and security. We know memory safety, Rust is it, will be the solution. But coming from a security world, my first question is, where are the gaps and where are we lying? We say we're memory safe and everything, but there's boundaries to memory safety, and I want to answer those questions. So the question of why am I asking, dude, where's my C? And it comes down to the fact that Rust is a language. When we write, strict Rust code, and it's only Rust code and it's all safe, then we have memory safety guarantees. But that's not the way the real world works. The way the real world is, and if we want to see Rust grow, and from any real use cases, it's the interactions with existing unsafe code. That's going to be where the security vulnerabilities are going to come out, and that's where a lot of the questions arise on what are these boundaries, what happens at these boundaries, what guarantees can we have for them. If we look at the existing ecosystem, I'll get into some of the analysis that I did on that. Syscrates exist. I'm massively grateful to everyone that works on those, but when it comes to how are they implemented, how does FFI happen, how are we doing these interactions with unsafe code, it's the wild, wild west. Everyone does it differently. We've kind of, as a community, fallen on a structure of best practices that everyone kind of follows. At least we can all call them the same thing and call them Syscrates. That's nice. But when it comes to how do we build them, how do we link them, it's different everywhere. And that's where the question sort of started, where it's how are we actually doing all this? Where is all this actual code? And from a security background, my next question is, where's all the vulnerable code? Now I know that we're linking stuff, so where are the vulnerabilities in it? That kind of raises the question of what are the categories of unsafe? What am I really looking for? Right now, there's been a lot of focus, a lot of tooling, a lot of work, a lot of analysis on unsafe code. We have the unsafe code guidelines. We are building an understanding, and with myriad more tooling around, can we analyze unsafe code and say and give a certain guarantee that it is safe? But there's a whole other category of unsafety that doesn't have the tooling and doesn't have the insight, which is unsafe dependencies. We all know that within our bubble of safety, we're fine, but where are the boundaries of that? Where are we calling out to it? And there's all of these external libraries being pulled in different ways, and there's no actual answer to the question of I've written my unsafe code calling other unsafe code, but I don't know what guarantees happen there. To kind of give a little insight into that, part of the analysis was just doing regular how many instances of unsafe there are. We have tools like Cargo Geiger that can do this. I'm going to go into a tool painter shortly here that we had done. But this is a graph of the instances of unsafe code existing across all versions of all crates in all time across the entire ecosystem. So if you didn't know, we have about 20% of crates have a single or more instances of unsafe code. Moving down that, more than 5 instances of unsafe, 15%. And you can see it's a pretty linear progression for the amount of unsafe code, so being unsafe syntax, existing across the whole ecosystem. It moves up to ones with more than 1,000. These are interesting ones. If we go to the tops, you can see most of the tops are exactly what we'd expect. These are things with unsafe code. The Windows crate, auto-generated unsafe code to call, all of the various Windows APIs. Red Rust LPN, you can see these are all the usual suspects we'd expect. And kind of walking into this, that's why I want to know what are the other libraries that we're using that are getting linked in. From the perspective of unsafe code, we have the tools and we know we're creating the FFI boundaries. We have libraries. There's the Foundation Interop Initiative, which is trying to help kind of solidify what does that boundary look like and how can we unify interop on an FFI boundary for making it more safe and just easier to use in Rust. But it still raises the question of what are we doing? So like I said, the unsafe syntax, though, when I'm looking at this, it doesn't actually tell me anything about vulnerabilities and safety. It tells me that there's places to look, but it's just an indicator. It's not something I can actually use to say that this crate is safe or this crate is unsafe. As a community and ecosystem, we've had some instances of that with very popular crates having a lot of unsafe code and actually having unsoundness within it. But from a security perspective, when I'm looking at it, I can't actually say there's a lot of unsafe code in this, so don't use this thing. I need to be able to give the guarantees on that. But when looking at all of this data, I could say that, highly unsafe crates, like you saw on the top, it's the Windows crate, it's systems level libraries, it's machine level libraries. These are places that I expect unsafe. So the metric isn't really that useful when I'm trying to figure out, where are the vulnerabilities within the ecosystem. I did find some benefit in sort of the edge cases of both of these. Things with lots of unsafe code, interesting to look at. Things with 1, 2, 3 instances of unsafe, also interesting to look at. These are the ones that, I actually want to go review and see what did they need an escape hatch for. Or are they doing FFI? It might be a smaller amount. But it all comes down to the fact that doing this at scale across the whole ecosystem, it's about indicators and not solutions. I'm not going to be able to analyze all this unsafe code across the entire ecosystem. I can do it on a crate-by-crate basis. But when I'm looking at the entirety of things, I can't just have somebody go do a code review for absolutely everything. So I need to figure out how do I make this scale, and what does the unsafe code actually do? For example, the Windows crate, it's a bunch of wrappers around Windows libraries. So I know it's an FFI location, but analyzing for unsafe code everywhere else, I can't really say what it's doing. So then diving in more, I said, okay, I'll start going through and finding what are all the crates pulling in? Where is all of this FFI code existing? What do the crates look like? What are the sys crates? Who's doing this? And it actually becomes a really complex question. There is no source of truth to this information. If I just go based off of things named sys crates, comes out to about 3,000. If I want to start analyzing the build scripts or how they build, then I could say things that are actually using cargo flags from a build RS. That comes out to about 2,700. But then I could go further and see, is there C++ code vendored in here? Are they doing a custom build and then linking it in? That comes out to about 1,000. And then is it C code? Another 2,700. There's these varying levels of the fact that I'm trying to find all of the instances of the C code and the FFI boundaries, but there's actually a multitude of locations that I have to look and find it. And I have to hunt down for all of those if I want to say with any certainty whether something's actually safe or not. Part of this was also looking at final built artifacts. Ended up being the most useless scenario I'm looking at. I can analyze all these binaries and start pulling out that I see something that looks probably like OpenSSL, but then you throw LTO into the mix and I have to completely trash it. So this kind of led to how can I do this analysis in a meaningful way to find actual external non-Rust code linked inside of Rust binaries. And that's where Painter comes in. This is a project I've been working on at the Foundation for about 1.5 years now. To give a little history on it, from a security perspective, this started with the idea of the Foundation tech team sitting down and thinking, what can we do to get ahead of the other ecosystems when it comes to security at scale for the ecosystem? Since Rust, we talk about safety, we talk about this being a main priority, so how can we actually do this at scale across everything? And we had to look at the other ecosystems, and one of the things that first came to mind was the notoriousness of NPM audit, which Cargo Audit is slowly following in its path of everyone just turns off NPM audit. It is a joke among security people that NPM audit is one of the most useless things when it comes to finding vulnerabilities in your node code. And the answer to that is why is it fairly useless? And it's because of the noise. The noise level in NPM audit is completely unmanageable by anyone meaningfully trying to use it. And that noise comes from the fact that they're doing dependency checking, but they're not doing code checking. And so Painter is the solution we had to that idea in Rust, which is what if we could do full call graph analysis across the entire Rust ecosystem and not just answer, you have a vulnerable dependency that had a CVE or a RustSec vulnerability against it, but we can answer the question of, and you're calling the vulnerable function. And this could actually give us, a much higher level of certainty to reach out to people. And instead of just giving them, random reports of, hey, Cargo Audit said you had 50 vulnerabilities, we can say, Cargo Audit said you have 50 vulnerable dependencies, and among those, you're using 4 of the vulnerable functions. So that was the history and inception of Painter. So what did it end up being? It ended up being building a full graph database of the whole ecosystem, and to say it again, across all crates of all versions of all time. And out of that, we extracted not just the dependency graphs for that, but did sandbox builds of every single crate. And from that sandbox build, we actually do 3 stages of builds, do a full LTO build, do a full unoptimized build, all optimizations and LTO turned off, and then a third build of that does LLVM IR emission for the entire build of the crate. And from those 3 builds, then we can actually pull a full function level graph, do an analysis on the IR code, and start pulling out what are the function calls and what are the relationships of actual called code across the whole ecosystem. This also has the side benefit of giving us basically a pipeline to do other analysis across the whole ecosystem. Akin to kind of, Rust-wide and Crater allowing to do full Rust compiler tests across, if not the whole ecosystem, a large swath of it. This lets us say what are, all of the crates calling for, say, a crypto library or for a compression library. And we can now find the function for that version of that crate and that sys crate and walk the dependency and call graph backwards and actually say everyone that's using it. So right now, like I said, we've been working on Painter for about a year. It's now deployed to GCP and also running constant workloads against the entire ecosystem and on publish. So when we want to run experiments, we can actually do one across the entire ecosystem, and all of this data has already been pulled in. We can also run it on publish, so as new crates are published, we have these being built again and the analysis being ran again against that crate. We're also leveraging it for a separate project that we call Sandpit, and this is working with the Crates.io team on malicious crate analysis. So from a security perspective, we have all of this IR sitting around and these call graphs sitting around, so why not use it to also find, nasty stuff happening in the ecosystem? Final side benefit of that is because we're doing all of these builds, then we also get to see the actual build process in a sandbox. OpenSSF has their own project for this, for doing builds across all of the repositories of all of the ecosystems. And so, we've basically mirrored that inside of Painter with Sandpit, where we can do analysis of the actual build process. So that's Painter. That's how it was conceived, being that we just wanted to say how do we make cargo audit better. But then past that, because we have this tooling and this entire pipeline to do analysis on the entire ecosystem, I wanted to use it specifically for this topic. What are all the C libraries? What's getting linked in? What is the FFI boundary? Within Painter, this gave us a few avenues to at least start collecting that data. If you recall, it was that there is no source of truth. I can't just go to a build RS and say, yo dog, what is all the C libraries you're linking? Everyone does it differently. So from that perspective in Painter, we added monitoring to the actual build processes in those sandboxes. So I can monitor for, what are the Rust C flags getting called on execution? Are they linking in new libraries? I can also monitor, the actual command execution of build RS. So, as build RSs are running, I can see, are they running GCC? Are they running Clang? And I can at least use this as a trigger to know that this is a sys crate and it does have external stuff. Determining what those external things are is a whole other problem. Since it's going to be various libraries, they might be vendoring their code, they might be downloading it, that one gets interesting. But at least we can start building this picture of what is the full FFI external library story here. From the IR analysis perspective, this lets us do calls into dynamically linked code. We can walk through the IR, and from a bare simple perspective, we know Rust C is generating our IR, but if we do it pre-optimization, then it is not pulling in C libraries. So it's a general good guess that anything that's calling to a function that I don't currently have in my IR code is an external function. So that allows me to start mapping it that way. I can also detect calls into non-Rust objects. This is the case of I believe that it came out to about 13% of syscrate builds, being that it vendors code, but also links in its own wrappers for that vendored code. And so I have this mixture of a vendored actual lib file and some custom objects that were built independently and Rust code, and these are getting linked in at different mixtures. And so I can at least detect that those are occurring. And finally is the call graph that we've actually built. I can just look at my call graph and see what are things that I know aren't Rust libraries or it's not Rust mangled. Then I also know that this is another, at least external library, possibly C, could be anything. The other methods of going through this is build RS. We can go through watching the execution of build RS or parsing it with SYN and see, is it emitting cargo flags? Is it calling in C, or is it using CC dependency to actually do builds? Is it doing command calls to, like I said, GCC, Clang, CMake, make? Here are all the other methods that a C library might get pulled in. And then finally, a source analysis, both on build RS and on the entirety of the crate. And this is walking it through Rust Analyzer and SYN and analyzing, does it have link args being pulled in? Does it have a bunch of extern stubs that it's using to link things in? And this at least lets us start drawing a picture of what this looks like. The results were actually rather unexciting. It was exactly what I walked into this expecting, which is libc, libstd, libstd, C++. These were things I was expecting when it came to external C libraries. Windows library is also another big one, but what it really came down to was crypto libraries and compression libraries. This was the majority of the actual C code coming in to the ecosystem as a whole. And if you think of it as when I say the most, this is not the most of independent crates linking in many compression libraries or many crypto libraries, but this is the dependency tree of the ecosystem. Within all of our ecosystem and our community, what is everyone depending on down at the bottom at the core? And it all comes down to crypto libraries and compression libraries. They came out to 85% of the C code getting linked in. We have the outliers, but from an ecosystem perspective, since we're looking at a dependency tree, I can't say that there's a lot of production usage of this one arbitrary crate that is a binding for a C++ library. But I can say they all probably depend on a compression crate. From mismatches, among those, it was 85% of the compression and crypto libraries. Underneath that, mismatches came out to about 7% when building across the entire ecosystem with crates linking in multiple versions. The majority of this being that it was semver mismatches. And the semver mismatch problem is people trying to follow the versioning of external C libraries, which does not match the semver rules that we use within Rust. And you'll run into these scenarios where then they have matching version numbers for the actual crate name, which then pulls in multiple versions of these libraries. So that is, we found out that C libraries are basically everything that we expected, but it's really hard to figure out what they are. And from a security standpoint, from a compliance standpoint, and from a certification standpoint, if we're talking safety critical, we need to figure out how can we actually identify all these across the ecosystem, and what can we do to make this easier, and what can we do to not just allow filling my security little heart with joy and figuring out what everything is and filing CVEs and getting things updated, but what can we do to help the ecosystem and actually help all of these maintainers do this more efficiently, do this easily, and is there a way that we can get both sides of this working out? So among these, I'm going to work through 4 items that kind of came out of this of what are the things that we want to do to make this better. The first one is a unified build framework. This is something we've been kicking around at the foundation on the tech team for the past year since Unconf last year. Unconf last year, there was a lot of interest in the concept that doing build RSs is hard, and doing them correctly is even harder, and everyone does them differently. So, we're kind of doing a call to action / me and Adam Harvey at the foundation are beginning to work on the concept of what if we made the one build RS crate to rule them all that everyone can pull in as a build dependency and uses the glue of, CC and CMake and all of these other crates that exist that are already there that we really just need to shove together in a unified way that then makes it easier to analyze. From my side of things, I want to be able to have an automated way that I can just look at a crate and say, it has a build, and this build is pulling in these C libraries, and it's building them this way, and that's all I need to worry about. So from a implementation standpoint, we're thinking about, is there a way we can make this machine readable? Are we talking about just making a build RS crate that follows a builder pattern that then we can easily parse with SYN? Or if we do that as a stage 1, is there a way we can make this a declarative language? This also ties into other interesting discussions within the project as a whole of what happens if we could make this such a declarative framework that crates don't even need to actually use a build RS. What if they make a build TOML? And then this ties into sandboxing discussions of build RS, where if we have a build TOML, then making a sandbox is a lot easier since we have a declarative way to define what that sandbox needs to do. It's a hard problem. Like I said, everyone does it differently. We are building on the shoulders of giants that like to do everything their own way in the C community, and figuring out a way to do a good abstraction, building on top of that and making it platform and environment agnostic is going to be a hard problem, but we think that it's a worthy problem to try to solve. We tend to joke that there's the 80-20 problem here. The 80% of the crates out there are going to take up the least amount of time, and that final 20% is going to take 80% of our time. So we're hoping to be able to at least get that coverage of that 80%, and get the full build framework to a point where the majority of sys crates out there that are doing basic C library wrapping can get pulled in via this method, and we can have a declarative syntax for it. But that opens the question of who's going to do all the work, because I don't want to run around filing a bunch of bugs on maintainers and pissing them all off, saying, hey, you need to do this extra work because I told you so, pretty please go do it. And that comes to the next item, which is how do we help the ecosystem, not just say, you should use our unified build framework, but how do we help them as a whole as the syscrate maintainers, are working to maintain their libraries. XZ is the one we all talk about where, what happens if we get a malicious maintainer in there. So, this is not just from the what are my C libraries, but how can we help make C libraries more secure? How can we reduce the CVEs, and how can we help them maintain them? And first item of this being that, that there are high-use, high-risk syscrates out there. Figuring out what they are is something Painter's specifically designed to do. We can at least say that these are the high-dependency ones, and I'm sure we've all seen that XKCD article of that one guy in Nebraska that is the building block for everything else. CVE monitoring and automation and updating is something else that we're also looking at. Is there tooling that we can do across the entire ecosystem on GitHub? We also have a separate project within the foundation, which is explicitly determining Git provenance for crates that exist in the ecosystem. And one of the cool side benefits of Git provenance is if we can identify the Git repo of every single crate that exists in crates.io, we can now automatically spider to that, figure out who the maintainers are, contact them, file issues, file pull requests with them, and have a tool chain to start automating, helping the ecosystem, keeping this all maintained. This also comes down to the social, financial, and I've already spoken on the technical sides, but actually building relationships with these high-use, high-risk crates within the ecosystem is also going to be critical for us. And figuring out, what tooling can we build to help? I mentioned Git provenance, but what do we do with it? And we don't really know yet, but this is something we're trying to start figuring out. Other ecosystems are also struggling with this problem right now. OpenSSF and Alpha Omega both have very large, very well-funded initiatives trying to answer this question. But going all the way back to the beginning, when I mentioned the history of all of this, is we're trying to approach this as, how can Rust get ahead of the curve, and how can we do this better than everyone else is already doing it, and can we help be the leaders in doing this? And this all comes down to the ecosystem sustainability. We've always been a very welcoming and a very sustainable community, so can we continue that when it comes to this problem? Another solution to all of this is that dynamic linking has kind of been the bastard stepchild of Rust for a long time. It's not the way that we do things by default, but when it comes to the rest of the programming communities and operating system platforms, distributions, dynamic linking has historically been the solution to sort of the update problem. When we think of all of these C libraries, they're generally statically compiled into Rust, which then is all statically compiled single binaries, and it makes it really hard to update. You have to re-update and redeploy anything when you're doing a security update. So we're kind of looking at how can we make dynamic linking a better, more sustainable story. This might be solutions like Krabby, which was API or ABI for Rust to do possibly leverage that for dynamic linking. We have the interop initiative at the foundation looking at interop in general with C++, but maybe the story leads towards some sort of new ABI dynamic linking story for Rust. I could see the build framework being useful for this. If we can make dynamic linking for Rust at least easy to build, then maybe that's something that would help start moving things that direction. And finally, looking through all of this is, there's going to be changes that, we're going to want to make within Cargo specifically. There's a few initiatives that, are already happening within the Cargo team and the compiler teams, but things like emitting SBOMs, but emitting useful SBOMs. If you're not familiar with sort of the problem everyone's running into with those right now, is the fact that SBOMs will just tell you everything in the kitchen sink that currently exists in your code base, but it's emitted for everything. You don't actually emit what's in the final binary unless you're doing this post-LTO. That is what Omnibor was from CISA is kind of trying to solve. What does that picture actually look like in the real world? And that's something that, when it comes to the SBOMs currently at least being discussed within the Cargo and compiler teams, that's something we should be thinking about with that. And past that, from my personal experience, implementing all of this in Painter, is that there's a lot of emissions and instrumentation that could be implemented in Cargo and in Rust C that would be information that I would find useful. And I know Omnibor would find useful, and anyone else doing this kind of analysis would be useful. A lot of that being around non-Rust code linkage. What is actually getting linked in? Can you please emit more artifacts besides the IR for me? And those changes are, generally having to do with optimization passes and wanting to inject myself at different points in optimization to get different points of data I want. From the full changes within cargo in the compiler, I'm not sure what that picture actually looks like, but it is, one of those things that, I'm going to begin reaching out to people on, pretty please at least send me this emission. And those are kind of the overall changes that I want to make, and that sort of ends my talk on all of that. But, like I said, this is also sort of a call to action on help to that. Me and Adam don't want to build this build framework, in isolation by ourselves, so we'd welcome help with that, as well as the instrumentation and code changes that we're kind of looking to do. So thank you.